Hello students, welcome to my YouTube channel. In this video lecture, I am going to answer questions from sample paper number 3, RK Bali navigation book. So let's begin. Question number 11. Correction, question number 21. On a Lambert's chart, whose standard parallels are 37 degree north, 65 degree north, with respect is the straight line drawn on a map between positions 49 degree north, 30 degree west, 48 degree north, 40 degree west. The great circle and rhumb line are to the south of the parallel of origin. Great circle and rhumb line are to the north of the parallel of origin. Great circle is to the north, whereas rhumb line is to the south. So let's draw this Lambert's. Let's consider this is your Lambert's charts. The two standard parallels are 37 north and 65 north. So this is your 65 north and this is your 37 north. Okay, these are your standard parallels. Now the parallel of origin will be the average of these two standard parallels, which is equal to 65 plus 37 divided by 2, 51 degree north. So 51 degree north will be your parallel of origin. Now now when you look at the properties of Lambert's chart, the great circle will always be to the north of the parallel of origin if you are in the northern hemisphere, meaning the great circle will always bend away from the parallel of origin, will bend away from the parallel of origin. That means it will be concave to the parallel of origin, convex to the nearest pole. Rhumb line, contrary to that, rhumb line will bend towards the parallel of origin, meaning it will be convex to the parallel of origin and concave to the poles. Okay. So now here there are 2 points given to us. So just to show you, the great circle will be somewhat like this, away from the parallel of origin, and rhumb line will be towards the parallel of origin. So this will be your great circle, this will be your rhumb line. Okay. Now let's look at the positions given to us. 49 north and 48 north. 49 north, 49 north and 48 north. And one is in the A is to the east of Bravo. So now the great circle joining this. Now since parallel of origin is above both the points alpha and Bravo, what will happen? So the great circle joining alpha and Bravo will be away from that parallel of origin. It will bend away from it. So it will be something like this. Okay, this will be your great circle. Rhumb line will be towards the parallel of origin. So rhumb line is here, parallel of origin, close to the parallel of origin. Great circle is away, bending away from the parallel of origin. Okay, so the correct answer here will be great circle and rhumb line are to the south of the parallel of origin. Yes, this is your parallel of origin. Both rhumb line and great circle are to the south of it, below it. Right? So option A will be the right option. Next, maximum allowable crosswind component is 20 knots, runway 06, runway QDM 063, wind direction 100 magnetic. Calculate the maximum allowable wind speed. So the crosswind component is equal to wind speed into sine theta, where theta equals to wind direction minus runway direction. Wind direction is 100 magnetic, runway direction is 063 magnetic. So 100 minus 63 is equal to 37. So now the crosswind component given to you is maximum crosswind component is 20 knots. Wind speed is what we have to find out. Sine theta, sine 37. So wind speed will be 20 divided by sine 37. 20 divided by sine 37. 33.23 knots. 33.23 knots. So the closest option here is option alpha, 31 knots. Okay. 31 knots. So let's draw this diagram. Consider this is your north datum, runway 06, and opposite is runway 24. The winds are coming from 100 magnetic. So winds are coming from 100 magnetic. So wind velocity is 100 magnetic at 31 knots. So this particular wind will have a maximum crosswind component, or will produce a maximum crosswind component of 20 knots. Next, question number 23. Distance Q to R, total distance departure to destination to 2160 miles. Ground speed, outbound speed, homebound speeds are given, endurance is given. What is the distance from departure to point of no return? So distance to point of no return is endurance multiplied by outbound speed multiplied by homebound speed divided by outbound plus homebound. So endurance is 6 hours, outbound speed is 535, homebound speed is 585 divided by 535 plus 585. 535 plus 585 is 1120. 6 into 535 into 585 is 1877850 divided by 1120 is 1677 nautical miles. So distance to PNR is 1677 nautical mile. Option brown. Simple formula based. True course is given, distance is given, task is given, winds are given. Departure time in UTC is given to you. What is the arrival time? Now to find arrival time, we must know ground speed of your aircraft. With that ground speed, with ground speed and distance, we will calculate total flight time. And with that flight time, we will calculate arrival time. So first we will use CX3 to calculate ground speed. So step 1 ground speed. Use CX3. So okay. So go to wind correction option. True airspeed is 450. True course is 250. Winds 200 at 60. So this check the values once again. As 450, course 250, 00 at 60. Okay, so this gives a ground speed of 409 knots. A ground speed of 409 knots. Step 3, correction, step 2, time. Flight time will be distance by speed. Distance 315 nautical miles divided by 409 knots. So 315409. 46 minutes. 0 hour 46 minutes. Step 3. Estimated time of arrival equals to estimated time of departure plus flight time, journey time. So departure is 0650 plus 0 hour 46 minutes. So 6 hours 50 minutes plus 0 hour 46 minutes is 7 hours 36 minutes UTC. So you will reach your destination at 0736. As pressure altitude increases, temperature decreases then remains constant, temperature increases then remains constant. Now in the ISA atmosphere, beginning from mean sea level up to 36,050 feet something, your temperature decreases. Temperature decreases at a lapse rate of approximately 2 degrees Celsius every 1000 feet. Above 36,000 feet, the temperature remains constant at minus 56.5 degrees Celsius, minus 56.5 degrees Celsius, up to up to some 65,000 feet. After that, the temperature again starts increasing. In the mesosphere, stratosphere, it starts decreasing. Mesosphere again, it starts increasing. So decreasing correction. So this is the ISA property, ISA characteristic. Temperature starts decreasing from mean sea level up to 36,000 feet. From 36,000 feet to 65,000 feet approximately, it remains constant at minus 56.5 degree Celsius. So the correct answer here is option Bravo. Temperature decreases, then remains constant. Then remains constant. Okay. Question 26. True altitude is obtained from what? Density altitude, temperature altitude, pressure altitude. Okay. So true altitude is obtained from two things: temperature, non-standard ISA temperature. You have to apply that correction, and you have to apply barometric pressure correction. Okay, so the closest answer here is option Charlie, pressure altitude. True altitude is obtained from pressure altitude. Okay, there is no such thing called temperature altitude, and density altitude is connected to pressure altitude, not true altitude. So alpha is also wrong. I have solved so many lectures uh, in which I have calculated true altitude from pressure altitude. Okay, so there are many questions in which you have to calculate true altitude, taking into account non-standard ISA temperature, pressure. I have also solved Oxford Meteorology Altimetry questions in which I have calculated true altitude numericals. So do watch all that video lectures. If you haven't yet, you will find those lectures in the playlist sections that I have made. So I have put all the lectures in separate playlists, in relevant playlists. You will find Oxford GenNav playlist, RK Bali GenNav playlist, Oxford Meteorology playlist. You will find meteorology sums in that playlist. So just explore the channel. You will find the relevant videos. Next, question 27. During a straight and uniform climb, the pilot maintains a constant calibrated airspeed. So what will happen to Mach number and true airspeed? So I have answered this question multiple times. Let's say you are flying in a particular air mass. Okay, let's say this is that air mass, and you are climbing to higher altitudes. You are climbing to higher altitudes at constant constant calibrated airspeed. Now, as you fly to higher altitudes, atmospheric atmospheric pressure decreases. Atmospheric pressure decreases. Now, your airspeed indicator is a pressure instrument. Is a pressure instrument. It uses what kind of pressure to show airspeed? It uses dynamic pressure, and this dynamic pressure is shown to us in the form of indicated airspeed. An indicated airspeed corrected for position error, pressure error gives us calibrated airspeed. Okay, so calibrated airspeed. Now, in order to get calibrated airspeed shown to us, the airspeed indicator depends on atmospheric pressure. Now, atmospheric pressure is nothing but static pressure, dynamic pressure. Now, when your aircraft climbs to higher altitudes, outside atmospheric pressure goes on decreasing. If outside atmospheric pressure goes on decreasing, the airspeed indicator will have less and less atmospheric pressure to register, and less atmospheric pressure for registration, that means less and less uh, representation of airspeed. So if you have less dynamic pressure getting registered in your airspeed indicator, direct impact will be on the calibrated airspeed shown to you. So calibrated airspeed will also decrease in value. If pressure decreases, dynamic pressure falls. So calibrated airspeed value also falls with it. So that is the side effect. So in order to have, you may be flying at a constant speed, constant true airspeed, but the calibrated airspeed shown to you will start falling as you go to higher and higher altitudes, because the pressure available at those altitudes goes on decreasing. So in order to prevent your calibrated airspeed from decreasing or from falling, in order to maintain a constant calibrated airspeed, let's say 200 knots as you climb to higher altitudes, and to prevent it from falling 200, 180, 170, so on and so forth, what will you have to do? You will have to increase the true airspeed of your aircraft. You will have to increase the true airspeed of your aircraft. When the task or true airspeed of your aircraft increases, dynamic pressure, dynamic pressure or impact pressure around the pitot tube also increases, right? Now this additional dynamic pressure, this increment in dynamic pressure will compensate for any decrease in static pressure as you climb to higher altitudes. So that's why we are deliberately increasing the true airspeed of your aircraft to get additional dynamic pressure which acts or which compensates for any decrease in atmospheric pressure as you go to higher altitudes. So therefore, if you want to fly at constant calibrated airspeed, increase the forward speed of your aircraft, true airspeed of your aircraft. So option A, Mach number increases, TAS increases. Option Bravo, Mach number constant, TAS constant. Charlie, Mach number constant, TAS decreases. So the only correct option here is option A. True airspeed increases. Now what is Mach number? Mach number is nothing but true airspeed of your aircraft, true airspeed of your aircraft divided by local speed of sound. Correct? Divided by local speed of sound. So Mach number is proportional to true airspeed, inversely proportional to local speed of sound. So now as you go to higher and higher altitudes, what happens to atmospheric temperature? Atmospheric temperature goes on decreasing. Atmosphere temperature decreases. And we all know that local speed of sound is nothing but 39.17 square root of absolute temperature. So that means it's proportional to temperature. So if temperature decreases, local speed of sound will also decrease, right? So if local speed of sound decreases, automatically Mach number will increase. So local speed of sound is decreasing on one hand. Your true airspeed as you climb at constant calibrated airspeed increases. So the overall effect on Mach number is that Mach number will also increase. Okay, so as local speed of sound goes on decreasing as you go to higher and higher altitudes, and as goes on increasing as you climb to higher altitudes, the margin between true airspeed and local speed of sound goes on decreasing. As the margin between them decreases, Mach number will increase. What is Mach number? Mach number is nothing but true airspeed as a fraction of local speed of sound. So if local speed of sound is decreasing, true airspeed is increasing. So the margin or the spacing between them decreases, and slowly and slowly true airspeed and local speed of sound at some point of time will become equal to each other. And when they become equal to each other, we say we have achieved Mach 1. Okay, so the correct answer is Mach number increases, TAS also increases. For a constant calibrated airspeed and a level flight, a fall in temperature will result in what? So this is a little different sum. So let's say you're flying in a particular air mass. This is your initial air mass where the temperature is 30 degrees Celsius. From this air mass, you enter a new air mass which is colder than that, and the temperature in this air mass is 20 degrees Celsius. You are flying a level flight, you are not changing your altitudes, and you are flying at constant calibrated airspeed. Flying at constant calibrated airspeed. Let's say 200 knots, 200 knots, okay? And a level flight, let's say you're flying level at 10,000 feet, 10,000 feet. Now let's calculate true airspeed. True airspeed in warm air mass, true airspeed in cold air mass using CH3. Let's go to airspeed option. Outside temperature in Celsius, convert the unit. So first warm air mass 30 degrees Celsius. Calibrated airspeed I have considered 200 knots. Pressure altitude I think 10,000 feet. Yes, 10,000. So now with a pressure altitude of 10,000, calibrated airspeed 200 and 30 Celsius. Yeah. So CAS 200, altitude 10,000. Outside air temperature 30 degrees Celsius, you get a true airspeed of 246 knots. 246 knots. Now, a different air mass which is 20 degrees Celsius, colder than 30. So, 20. In that case, your true airspeed is 242 knots. 242 knots. So, what has happened? When you travel from warm air mass to a cold air mass, true airspeed decreases. 246 has become 242. So, the answer will be lower true airspeed due to decrease in density, lower true airspeed due to increase in air density, higher true airspeed due to decrease in air density. So we have lower true airspeed. This part is right, both in both the options. What happens when you go from warm air mass to a cold air mass? In warm air mass, air is less dense, air is thin, whereas in cold air mass, air is more dense or denser than air in warm air mass. Okay, so the correct answer here will be option Bravo, due to an increase in air density. Next, if ambient temperature is minus 10 Celsius, what is the Mach number when TAS is 594? Now you can use your CH3 and calculate this. I will show you the formula method. Now Mach number is true airspeed divided by local speed of sound. Now true airspeed is 594. Local speed of sound is 39.17 square root of temperature in Kelvin. So that is equal to 39.17 square root of minus 10 degrees Celsius plus 273 is 263 Kelvin. Mach number will be square root of 263 multiplied by 39.17, which is 635. So 594 divided by 635 is 0.935. Okay, so select that option which is closest to this value. Question 30. What is true Mach number at 25,000 feet ISA conditions if true airspeed is 500 knots? So similar to the previous question, but here we have to first find out the temperature, ISA temperature at 25,000 feet. Now what is the ISA temperature at 25,000 feet? 15 degrees Celsius minus 2 into altitude 25,000. So 2 into 25. 15 minus 50 is minus 35 degree Celsius. Now minus 35 degrees Celsius is equal to 238 Kelvin. So task 500, 39.17 square root 238, 500 divided by square root of 238 into 39.17, which is 604. 500 divided by 604 is 0.83. 0.83. This concludes our lecture. I hope you have understood all the 10 questions that I have solved in this video lecture. If you have any doubts or questions, let me know in the comment box of this video lecture. In my next video lecture, I will solve the remaining questions. So don't miss that lecture. I will see you there. Best of luck.